All right, how's it going? How'd the programming assignment work out? Okay, that's fair. Yeah, I've written tons of code in my life that I've never wanted to look at again. Some of it is still being used. But yeah, you know, sometimes you just get it working and it's like that's the goal. All right, cool. So any questions? Go ahead. Okay. Okay. Like F composed with G composed with H? Yeah, like that. Okay, let's make something up. So let's say f of x equals x squared. And let's say g of x equals, how about x minus 5? And let's just mix it up. Let's say h of x equals sine of x. Do some trig. And let's find h compose g compose f. Okay, well this is h composed with g composed with f. It means apply f and then apply g and then apply h. Okay, it goes in that direction. So this is actually h composed with g of f of x is x squared, which is h composed with, what is g of x squared? Well, g of x is x minus 5. G of x squared should be x squared minus 5. And what is h of x squared minus 5? H of x is sine x. H of blah is sine of blah. So h of x squared minus 5 is sine of x squared minus 5. And just for fun, if we compose in the other direction, f of g of h of x, well, that's f composed with g of sine of x. And g of x is x minus 5, so g of sine x is sine of x minus 5. And f of anything is anything squared, so this is sine of x minus 5 quantity squared. And in general, when you switch the order of composition, you get something totally different. Does that help?
Yeah, it helped a lot.
Okay, cool.
7.1, number 2C.
What does it say?
I guess the 3 right down.
Okay.
The one we have like A bracket like 1, 2, 3. We have like x sub b and x sub a. You feel like finds it functions that massive to it.
It's asking for x sub a and x sub not, or
Hmm.
x sub b.
All right. I better look it up because I'm playing high-low here. Not bad. All right, 7.1. Section 7.1.
Yeah, 7.1, number 2C.
7.1, 2C. Did I really assign that? Oh, I did. Yeah, I remember this. Okay, so we're told that if S is a subset of A, we can define this thing called a characteristic function, which is chi sub S, which goes from A to the set 0, 1. And this is equal to 1 if A belongs to S, 0 if A does not belong to S. So it's a membership function, basically. It eats an element in A, and it tells you whether it belongs to S. So we're asked, let A equal this set containing A, B, C. So chi of the empty set, yeah, that's the empty set. Does that help? Yeah, there's multiple symbologies sometimes. So chi of S says is an element, a member of S. So chi of the empty set of A is going to be 1 if A belongs to the empty set and 0 if A does not belong to the empty set. Doesn't matter what A you pick, it's not a member of the empty set, so this is always 0. So this is for all A and A. And then chi sub A is going to be 1 if A belongs to the set A and 0 if A does not belong to the set A. And for any element of A, any little a that belongs to the set A, it's going to be an element of the set A, right? So this is necessarily going to be 1. So this is just saying there's no elements in set A that belong to the empty set. This is saying every element in set A belongs to set A. So it's a kind of quirky way to define 0 and 1 functions.
This was 2C?
This is 2C. For the first one? Yeah, so you could write it as this. Yeah, so that's a perfectly fine way to define the function. And the second one would be same thing, but the second element is 1. Other questions? All right, so let's talk about mathematical induction. And this is really a key part of CSE 215, is understanding induction for a few reasons. One, it's a really powerful proof technique that we can apply to lots of situations, some involving numbers and equations, some involving horses. It's applicable to a lot of different things. Two, it lets us formalize something that we already kind of do ourselves when we think about a situation and we decide whether it's true or not. A lot of times we're applying mathematical induction in our heads. And so when we want to prove something that we believe is true and we've convinced ourselves is true, sometimes this is the machinery we can use to actually formalize this into a rigorous proof. Three, it ties in directly to computer science. A lot of what we're going to be doing in the remainder of 222 and throughout 223 is what's called recursion, recursive programming, having functions that interact with themselves. And it's really a computer science analog to this concept of mathematical induction. And we can use induction to understand when recursive functions are correct or when they're not correct, and to understand what they do. So it's not going to look like all of those things initially. Okay, it's going to look very formal and very kind of mathematical, but it will be something we come back to again and again, and it's going to be really useful. So let me give you the very sort of stuffy formal definition of mathematical induction. So let P of n be a family of propositions and n is going to be an integer, and n is going to be bigger than or equal to 1. This isn't strictly necessary. It's got to be an integer. It doesn't have to be bigger than or equal to 1. It could be bigger than or equal to 0 or 100 or -5 or any fixed number. But it's got a lower bound. Okay, so generally we'll have n bigger than or equal to 1, sometimes 0. But for the definition, I'll just say n bigger than or equal to 1, but we can adjust it. Okay, so we've got a family of propositions. It's an infinite family of propositions. P of 1 says something. P of 2 says something. P of 5 says something. Okay, infinite family. Each element is a different proposition. Suppose we're given that P of 1 is true. So whatever this proposition is, we know that P of 1 is a true statement. And suppose the following implication. If P of n is true, then P of n plus 1 is also true for all n bigger than or equal to 1. So we're told P of 1 is true, and we're told one more thing. We're told if P is true for n, it's true for n plus 1. Now we're not told that P of n is true. We're told if P of n is true, then P of n plus 1 is true. That's what this statement is saying. So we're supposing that that if-then statement is provable. Okay, if we know these two things together, then we can conclude P of n is true for all n bigger than or equal to 1. Okay, soak this in for a minute. So we're not assuming that P of n is true. The only particular P that we're asked to show is true is P of 1. And then we're asked to show this if-then statement, that if P of n is true, then P of n plus 1 is true. But taking those two things together, we can wave our magic wand called mathematical induction and conclude that Pn itself is true for all n bigger than or equal to 1. Okay, so that's what we're going to be dealing with. So let me take our ladder example from yesterday and put this in terms of mathematical induction. So, example, let P of n be the proposition you can reach the nth rung of a ladder, of an infinite ladder. This is a ladder that never ends. And P of n is the proposition that you can get to the nth rung of that ladder. So P of a million says you can get to the millionth rung. Okay, so we have to figure out if two things are true. Is P of 1 true? Well, I'm going to say the ladder is sitting right there. There's nobody guarding it. You're totally free to go and stand on the first rung. Okay, so P of 1 in this case is going to be true. So is this proposition true? If you're on the nth rung, can you get to the n plus first rung? And again, I'm going to say the answer is yes, because you're able to lift one leg, put it on the next rung, move your hand up, and pull yourself up. So this is also true. Given that those two things are true, P of n is true for all n. What does this mean? It means that you can reach the nth rung of an infinite ladder for any n bigger than or equal to 1. You can reach the billionth rung. And the reason this is so powerful is because we didn't say anything about the billionth rung in this proof, right? All we said was something about the first rung of the ladder and something about wherever you are, can you go up one more rung? But we can put those together using the machinery of mathematical induction and conclude, therefore, you can get to any rung. Okay, now that's pretty obvious to us. We understand that if you can climb one rung and you just keep doing that a million times, you'll get to the millionth rung. But this lets you formally state that this is true. This is a proof that P of n is true for all n, assuming that you prove these two things. So before we start using this, let's think about why mathematical induction works. Casually speaking, if you want to know that P 100 is true, and you know these two things, you can do this in 100 steps. We start off by saying P of 1 is true, and then we apply this statement and say, since P of 1 is true, P of 2 is true. And then we do that again. Since P of 2 is true, P of 3 is true. And since P of 3 is true, P of 4 is true. And we know in our hearts that if we do this 99 or 100 times, eventually we'll be able to show that P of 100 is true. And we believe that we could extend this and do this for P of a million or a billion or a trillion. But of course, we can't actually write out a proof of P 1 trillion using this approach unless we write a trillion lines, right? And we're back to the monks in the cave moving disks. We'll talk about that later. It's going to take forever to do that. We don't have to do that if we know mathematical induction, right? All we have to do is know that this is true in P of 1, and we can conclude P of n. So it's doing something that we already kind of intuitively understand. And so let me mention some terminology. This is called the base case. Or sometimes the basis step. And this is called the inductive step. So the base case gives us a starting point. It gets us to that first rung of the ladder. The inductive step lets us move from there up however many times we want to induct. And both of these are absolutely critical. If P of 1 is not true, then we can't apply mathematical induction. And that should probably make sense to you. Right? Can I fly 1,000,000 miles away? Well, if I can fly this far, I could flap my arms again and fly this far, right? So if P of n is the proposition that I can fly this far, if P of n is true, P of n plus 1 is also true. but there is no base case. I can't fly this far. I can't fly any amount, right? So I can't prove that I can fly 1,000,000 miles because I don't have a base case. Okay, that's a silly example. And without the inductive step, obviously, all we've proven is P of 1. That doesn't say anything about P of 2 or 3 or 100. So you got to have both of these cases together. We can prove induction more rigorously. I don't want to get bogged down in it right now. I want to start playing with induction. But the basic idea is if there was these two conditions, if we know P of 1 is true, and we know Pn gives us Pn plus 1, but there's also some P big N for which P fails, right? We can basically work backwards a finite number of steps and get to either showing that P of 1 is false or there's somewhere where this implication doesn't work. That only works because over some set of n that are positive, there's a smallest element. And that actually gets into some strange set theory that we don't have to worry about. All right, so you got the setup. So let's prove some things with induction. So if we add consecutive integers, we get this series of triangular numbers, 1, 3, 6, 10, and so on. We talked about this a little the other day. And we might observe that 1 is equal to 1 times 2 divided by 2. 3 is equal to 2 times 3 divided by 2. 6 is equal to 3 times 4 divided by 2. 10 is equal to 4 times 5 divided by 2. And there seems to be a pattern here. So our theory is, if we were to add the integers from 1 to n, maybe we get n times n plus 1 over 2. That's our theorem that we'd like to try to prove. Okay, this does turn out to be true. So how do we prove this using mathematical induction? We have to state this as a proposition. Okay, so you got to go back to week 1. What is a proposition? It's a declarative statement with a truth value. This is not a proposition here on the left. This is not a proposition on the right. This equals statement is a proposition. And we want a family of propositions, so let's proceed like this. Let P of n be the proposition. One plus 2 plus 3 plus ... up to n equals n times n plus 1 over 2. And our goal is prove P of n for all n bigger than or equal to 1. And I don't have to keep saying prove P of n equals true. If I say prove P of n, it means prove it's true. Okay, it's like a C thing. Bless you. So let's prove P of n is true for all n bigger than or equal to 1 using mathematical induction. Well, to apply mathematical induction, we need two things. We need a base case and we need an inductive step. So base case, we want to prove P of 1 is true. Well, what is P of 1? What is the statement of that proposition? What does P of 1 actually say? Yeah, or if we don't simplify, or even less simple, 1 times 1 plus 1 over 2, which is the same thing. right? So this is 1 times 2 over 2 equals 1, and this is true. How do we know? Well, we have to believe that 1 equals 1. That's not always given, but we'll assume that in this course. So P of 1 is true. So we've done the base case. All right. The other thing we have to do is we have to prove P of n implies P of n plus 1 for any n bigger than or equal to 1. This is usually the step where you got to do more work. Base case is usually pretty quick. So we want to prove that if P of n is true, then P of n plus 1 is true. And we got to do a proof, chapter 3 type proof. So P of n is what we're going to assume. Right, this is our hypothesis. And working logically, using only the rules of logic and algebra that we understand, if we can show P of n plus 1 is true, then we've shown that given this hypothesis, we can reach that conclusion. In other words, this inductive step is true, and then we're done. Then we just say, therefore, by mathematical induction, P of n is true for all n. And we're finished. So we got to work logically from here and somehow get to P of n plus 1. Okay, this is a proof, which means that after I've written the hypothesis, which we're assuming is true, I can only write things that I know are true based on what I've shown. I can never write P of n plus 1 at this point. We don't know that P of n plus 1 is true. If I put anything down here that is the same as P of n plus 1, my proof falls apart. There's not much I can do here except maybe write out what P of n says. Right? We know what P of n is. It's this proposition, so I can certainly write down the following formula. This is the definition of P of n. Right, this is for some specific n. Well, what I'd like to do is prove P of n plus 1. So I'm going to do something. I'm going to mark off a little section on my page, and I'm going to say ignore. To make it really clear, this is not part of my proof. And over here, I'm going to write down what P of n plus 1 says. P of n plus 1 says if I add the numbers from 1 to 2 to 3 plus n plus 1, then I should get n plus 1 times n plus 1, which is n plus 2 divided by 2. Does everybody agree that's what P of n plus 1 says? All right, it's not part of my proof. I can't put this over here because there's nothing that proves that. But I'm putting it over here because this is what I want to show. If I can show that this equals that, then I can say that's P of n plus 1, therefore P of n plus 1 is true, and I'm done. So I'm putting it over here as a guide. And now I'm asking myself, if I know that this is true, how can I show that this is true? And we're back to solving puzzles, right? It's not really clear exactly what to do, but over here, I've got a piece of this thing that I'm trying to show. So the idea that comes to me is, what if I add n plus 1 to both sides of this? Right? I can add the same thing to both sides of an equality and it's still true. So I'm just going to try that. So step 3, 1 plus 2 plus 3 plus n plus n+1 equals n times n plus 1 over 2 plus n plus 1. And that's just good old algebra. I just added n plus 1 to both sides. Nowhere did I use this equality, right? If I use this equality, the proof is invalid because we don't know this is true. But I didn't use this. I looked at it for inspiration, but the only thing I did was add n plus 1 to both sides. Now I sneak a peek over here again and I say, you know, now this looks exactly like the left side of p of n plus 1. I wonder if this is actually the same as the right side. So we start doing some algebra and see if we can show that this is equal to this. So let's just do more algebra. So I'm going to do n squared plus n divided by 2 plus n plus 1. So I just expanded that top part. And n squared plus n over 2 plus 2 times n plus 1 divided by 2. So I'm finding a common denominator. And we're just going to town on algebra here. So n squared plus n plus 2n plus 2 divided by 2. So I distributed the 2. And now I'm going to combine like terms. So n squared plus 3n over 2. And then I'm going to factor. And without any trickery, I've shown that this sum up to n plus 1 is equal to n plus 2 times n plus 1 over 2. And that's all just algebra. And now I can look at the definition of p of n and observe that this equality is exactly the statement p of n plus 1. So p of n plus 1 is true, given that p of n is true. So therefore, p of n implies p of n plus 1 for any n, for all n. Therefore, p of n for all n by mathematical induction. So what have we proven? We've proven that this is equal to this for all n bigger than or equal to 1, which is what we were trying to do. So there's our QED. So there's a few pieces to this. Okay, let's break this down. We start off with what we're trying to show, right? We're trying to prove that proposition for all n. Well, let's go back further. We're trying to show that this formula is true, okay? So we wrote it in the language of propositions. We wrote a proposition for n saying that this is true, and then we wanted to show p of n for all n bigger than or equal to 1. And then we proved a base case, right? And then we tried to prove this inductive step. Pn implies p of n plus 1. And given those two, then we said, therefore, by mathematical induction, p of n for all n bigger than or equal to 1. And that proved what we were trying to show. So there's identifying a proposition. There's proving a base case. There's stating the inductive step. And then there's this legwork part of trying to go from Pn to Pn plus 1. And that's usually where the sort of real effort comes in. This is all kind of formalism. Base case is usually pretty straightforward. But this is where you really got to kind of like scratch your head and do the puzzle solving. And it's never totally clear from a problem what you're going to have to do here. It's usually pretty clear how to make the proposition. It's pretty clear what the base case is. And it's usually pretty straightforward to prove it. This is not well defined for a given problem. It takes practice. And we're going to look at a lot of different kinds of problems and see lots of different examples of what happens here when we're trying to prove this inductive step. So there's some formalism, and there's some intuition, and there's some luck in this process. And there's a mouse that doesn't like me. All right, still with me? Let's try a different one. So if we add consecutive odd integers, we get 1, 4, 9, 16, 25, 36. We get squares. So let's make a theorem, hypothesis, that if we add the odd numbers up to 2n minus 1, we get n squared. So let's prove this. So let P of n be the proposition that if you add the odd numbers from 1 up through and including 2n minus 1, you get n squared. We want to prove P of n for all n bigger than or equal to 1. All right, so what's our next step? Prove P of 1. Mm-hmm. So step 1, prove P of 1. All right, what does P of 1 say? Yeah, 1 equals 1 squared equals 1, and that's true. So we're done with our base case. If you're working with a friend, you say, I'll do the base case, you can do the inductive step. Okay, step 2, prove P of n implies P of n plus 1 for any n that we pick bigger than or equal to 1. So what does P of n say? So P of n is our hypothesis. What does P of n say? It says that. This is definition of P of n. So what should we do here? Say again? We somehow got to get n plus 1 squared. So let's do our ignore section. So what's the statement of P of n plus 1? So what's the next odd number after 2n minus 1? Yeah, which will turn out to be 2n plus 1, but yeah, that's a better way to do it. 2 times n plus 1 minus 1, exactly. So the left side of P of n looks like this, and the right side is n plus 1 squared. So what can we do to make some part of this look like some part of this? Add a what? I can add an n plus 1 squared to both sides. And I get that. But I'm not sure where we would go from there. What do you want to substitute? No. Because we're assuming that for some particular n, P of n is true. Right? So this is a frequent temptation. Just plug in n plus 1 and then write down what P of n is. But we're not assuming P of n plus 1 is true, right? Just P of n. So this is really assuming this for a particular value of n. So let's put a 2n plus 1 on both sides. Let's try adding this to both sides. So let's do 3 prime. Two n minus 1 plus 2n plus 1. And let's add 2n plus 1 to the right side as well. And now this left-hand side looks like the left-hand side of Pn plus 1. Does the right-hand side look anything like n plus 1 squared? It does. This is equal to n squared plus 2n plus 1 equals n plus 1 squared. And that's all just algebra. But what have we shown? We've shown that this sum is equal to this. And that's exactly what P of n plus 1 says. So P of n plus 1 is true. That's the definition of P of n plus 1. So P of n implies P of n plus 1 for all n bigger than or equal to 1. Therefore, P of n for all n bigger than or equal to 1. The reason is mathematical induction, and that's what we were trying to show. Are you believing there's something here? Let's prove n is smaller than 2 to the n for all n bigger than or equal to 1. I mean, this seems like it's true. 2 to the n gets really big really quickly, right? It's certainly got to be bigger than n in most cases. 2 to the 10th is 1,000. That's bigger than 10. 2 to the 20th is 1,000,000. That's bigger than 20. But how do we actually prove that this is always the case without doing too much mathematics? So we can do this using mathematical induction. So it's the same process. Let P of n be the proposition. So what's our proposition? N is less than 2 to the n. Okay, this is not our proposition. Don't say the proposition P of n is the statement that n is less than 2 to the n for all n bigger than or equal to 1, right? That's a much different proposition. That's saying that this formula is always true. P of n is just saying this formula is true for n. P of 5 says 5 is less than 2 to the 5th. Okay, so don't make the mistake of saying P of n is the proposition that this is true for all n. Okay, it's just true for n. So P of n says n is less than 2 to the n. So what does P of 1 say? 1 is less than 2 to the first, which is equal to 2, and that's true. So base case is done. All right, so prove That's step 1. Here's step 2. Prove P of n gets us to P of n plus 1 for all n bigger than or equal to 1. So step 1, P of n is true. That's the hypothesis. Step 2, let's write down what P of n says. It says n is less than 2 to the n. That's definition of P of n. So let me put my ignore area over here, and let's look at what P of n plus 1 says. It says n plus 1 is less than 2 to the n. Well, what can we do from here? This is really the only thing we know, along with P of n. Can we make this look somehow like at least some part of this? Let's add 1. Let's be as lazy as possible. N plus 1 is less than 2 to the n plus 1. Say again? No, that's the right direction. Okay.
If you had 2, right, doesn't that become 2n plus 1?
This is less than 2 to the n plus 2, but that's not 2 to the n plus 1.
Oh, okay.
But we know 2 to the n is bigger than 1. So n is less than 2 to the n, and we know n is bigger than or equal to 1. So we certainly know that 1 is less than 2 to the n. So if we add 1 over here, and we add 2 to the n over here, this is certainly going to be less than that.
Yes.
Right? And this is 2 to the n plus 1. So different kind of trickery here, right? But we've just shown that n plus 1 is less than 2 to the n plus 1, and that's P of n plus 1. Therefore, P of n implies P of n plus 1 for all n bigger than or equal to 1. Therefore, P of n for all n bigger than or equal to 1, which is what we were asked to demonstrate. So there's always something magic that happens somewhere in these proofs. Yeah?
Doesn't that 3 and 4 prove it for all for all n? Like prove that that P of n implies P of n plus 1 for everything?
Let's see.
Not that it's always true.
So if you started with a different base case,
Yeah, because doesn't the base case not affect recursion therefore?
correct. Yeah, so this might actually prove it for all n, except it's not true for n equals 0. Yeah, it is true. So this might actually prove it for all n. Say again?
What about n equals infinity? Wouldn't they technically be?
N has to be an integer, and infinity is not an integer, right? So infinity is we could say for all n, but that doesn't mean the same as for n equals infinity, right? So it's arbitrarily large n. We capture that saying infinity. Yeah, you might be right. The step might actually work regardless of whether n is bigger than 1 or not. Because, yeah, 2 to the n is bigger than n, yeah. And if you wanted to show this for all n using induction, you could do it in two pieces. You could show it for all n bigger than 0, and then show it for all n less than or equal to 0. Flip it around to make it positive.
That's not what I meant, though. I'm just talking about your first step, right? You're saying A of n is less than 1 isn't necessary.
Which one?
Your first step,
This one?
yes. The all n is not necessary in this case, but it is for the line below it.
I think I used it when I said that 2 to the n is bigger than 1. Right, I used the fact that n was bigger than or equal to 1.
Okay.
All right, so kick that over in the back of your brains. Tomorrow we'll start doing some non-mathematical versions of this. Yeah?
Other sets like the rational
The what numbers?
numbers.
It's got to be countable. There's probably other ways to do it, but the induction we're talking about has got to be countable. So you could do it on the rationals, yes, if you order them. But you can't do it on the reals. At least not like this, because there's no way to step up there.
Oh, yeah, because you can't say P and then plus 1 and it jumps over and stuff.
Exactly.